great pleasure to introduce the second talk. So Moritz Weber from Saarbrücken will tell us about quantum symmetries of graphs and their generalizations. I don't know whether we'll be generalizing symmetries or graphs or both.
Let's see.
Let's see.
Yeah, thank you very much for the invitation. Thank you for setting up this conference. So I will start with some family pictures. So there has been a conference on quantum groups and quantum information theory in the UK in 2015, and you can spot a few people that are here in the room. So let me enlarge this a bit. So here you see Adam, and who else is here?
Mike.
Here you see Christian, Mike, myself, Martin Lindsay, and here you see Hunhili. So there have been a couple of people on that conference 9 years ago, and so it has been in the air that we are the reason why this conference takes place here. So I think it's fair to say that this conference initiated this conference here. So I'm very happy about this, and I want to advertise another conference on quantum graphs. So this will be in February 2025 in Saarbrücken, and actually I predict that in 2034 we will have a conference here on quantum graphs, of course, so 9 years later. So this conference will not be organized by myself, it will be organized by Luca Jung, who's actually also here, my PhD student, and Daniel Gromada, my former PhD student. So if you're interested in that conference on quantum graphs, then just speak to Luca, who's here and trying to get an invitation. And then let me also announce that we will have a conference on Roland Speicher's 65th birthday on free probability in Saarbrücken. So this will be in June. Actually, his 65th birthday will be on 12th of June. So if you're interested in coming, so I'm the organizer for that conferences, I'm afraid. Mike is also one of the organizers, so speak to us. And then there's the saying, never stop a running gag, so okay. And anyhow, so this is some advertising about conferences. So let me come back to this conference here. So this is called New Trends at the Intersection of Quantum Information, Quantum Groups, Operator Algebras. So here's my understanding of these three main subjects. For me, quantum groups, that's quantum automorphism groups of combinatorial structures for this talk. Operator algebras are associated C-star algebras, and quantum information theory are non-local games arising from these combinatorial structures. And my main combinatorial structure will be graphs. So this is, I guess, well-known combinatorial objects. And then I want to speak about some generalizations of graphs and then highlight these three aspects: quantum groups, operator algebras, and quantum information theory. And actually, I decided to give a survey talk on results by my group. So I will not pick a single result, but I will rather give a small survey on what people did in Saarbrücken on this subject. Okay, so let me start with the graph case. So here it's based on quantum groups or quantum matrix quantum group. So it's called compact matrix quantum group, of course. Sorry. Compact matrix quantum groups by Voronovich. So for those who don't know the definition, here's the definition. It's a unital C-star algebra that is generated by certain elements uij, such that if you plug them into an n by n matrix, then this matrix must be invertible, and also the adjoints of these elements must be invertible, and there must be a star homomorphism of this kind. Actually, there's another typo on that slide, so this shall be capital N. Okay, never mind. So this is my understanding of quantum groups here. And then there's a main example by Shuzu Wang from the 90s, and there's the quantum permutation group, so Sn+, and it's given by uij's, which are actually orthogonal projections. So you see the relation of orthogonal projections here, and the rows and columns, they sum up to 1. This is the defining relations for the C-star algebra. You can check that it satisfies the axioms above. So it's a compact matrix quantum group indeed, and such a matrix, you can call it quantum permutation matrix, or you can call it magic unitary. And if you pick these uij's from m times m matrices, maybe this is the best way to think of these objects. So somehow I say that these quantum groups, they are matrices with matrix-valued entries. And the quantum permutation matrix, each of the entries is again an m by m matrix. And if you have m equals 1, then this is a classical permutation matrix. So why am I recalling this object, which many of you might know? Because this gives a way of permuting n points or n quantum points if you want. And if I speak about combinatorial objects, I have a discrete set with some extra structure. So I typically want to have the quantum permutation acting on the underlying finite set. Okay, so the quantum permutation group is my large group, and then I will add some relations depending on the combinatorial structure. For instance, for graphs, there has been a definition by Theo Barnica and Julien Bichon about 20 years ago. So you take this Sn plus C-star algebra and you add the relation that the magic unitary, or this generating quantum permutation matrix, shall commute with the adjacency matrix. So this relation UA equals AU. If you add this, then you get the quantum automorphism group of the graph. So this is theory from 20 years ago. Actually, I write these two names because they gave two different definitions. So this is the definition of Theo Barnica that I'm writing down here, but there has been a definition by Julien Bichon 2 years before, which is slightly different, and it gives a quantum subgroup of this, the one that I'm mentioning here. So I just want to mention there are two different definitions for quantum automorphism groups of a graph. And I'm mentioning this because in the quantum world, sometimes if you want to define a quantum object of something classical, you might have several ways of doing it, right? So this is the case here for this quantum automorphisms of graphs. And this will be relevant later when we speak about some generalizations, because there are more possible ways. Now, my PhD student, Julian Schanz, who's also here, so he did some work on the vertex transitive graphs on up to 12 vertices. So namely, if you have this quantum automorphism group of the graph, this is a subgroup of Sn+. You also have the classical automorphism group of the graph, which is a subgroup of Sn. And if they differ, if that's not the same, then we say that this graph has quantum symmetries. I also sneak in Bichon's definition of a quantum automorphism group, so that sits between these two. So you can ask for equality of these inclusions or inequality of these inclusions. So this is the existence of quantum symmetries, and Julian determined the existence of quantum symmetries for all vertex transitive graphs up to n equals 12. So for n less or equal 11, this has been done before by Julien Bichon and Theo Barnica in joint work, and then also by Simon Schmidt. Yeah, Julian did the case n equals 2. Take a look at this archive paper if you want to learn more about this, or speak to him, because, as I said, he's here, as you can see by this green green tag. Yeah. Okay, so this is something I wanted to mention about these graphs. So now the second part was operator algebras. Here are the associated C-star algebras. You know that to a graph you can associate a C-star algebra. This is almost 50 years old. So Kunz introduced the Kunz algebra and then generalized it together with Krieger to Kunz-Krieger algebras, and has later been generalized to graph C-star algebras. Here's the definition for graph C-star algebras. So it's generated by projections coming from the vertices. Then you have partial isometries representing the edges, and you have certain relations linking these projections and partial isometries. So I've spelled this out here. And here I'm using source and range of edges. So for me, if you see some edge, it comes from a source vertex and it goes to a range vertex. And you see in these relations, you have the projection onto the range and you have the projection onto the source at some point. Okay, so this is the graph C-star algebra. And now this conference is called something at the intersection of all these subjects. So intersecting quantum groups and operator algebras. Simon Schmidt and I had a result in 2017 where we showed that the quantum automorphism group of a graph acts on the graph C-star algebra, actually in a quite canonical way. And if you ask for other quantum groups acting in this same canonical way, on the graph C-star algebra, then you can show that this action is maximal. So in a way, the quantum symmetry group of the graph C-star algebra is the quantum automorphism group of the graph. Okay, so also this is a result which is not extremely new, but I mentioned this for these generalizations that I will come to in a minute. Okay, so this is about the operator algebras. Now for the non-local games, we have already seen the famous graph isomorphism game by David and Laura Manchinska and others. So you have the referee and you have Alice and Bob, and they are receiving vertices from one graph. They respond with vertices from another graph, and they win if and only if these answers and inputs have the same relation. So this means if you receive two vertices, if they are linked by an edge, the answer vertices also must be linked by an edge. If the input is the same vertex, then they must reply with the same vertex, and if they're not linked, they must reply with vertices which are not linked. Okay, so this is the graph isomorphism game, which we have already seen before, and also this is at the intersection of quantum information and quantum groups, as you know, because Alice and Bob win this game with a 100% chance, classically, if and only if the graphs are isomorphic. And this strategy actually comes from the permutation group, and they can use a quantum strategy, and they win 100% with the quantum strategy, if and only if the graphs are quantum isomorphic. And now this quantum isomorphism, this comes from this quantum permutation matrix, or if you want, the quantum strategy comes from the quantum permutation matrix. So you see quantum groups are involved in this non-local game, producing the quantum strategy. And Julian Schanz, which I mentioned before, in his PhD thesis, he also defined a switching isomorphism game, and here he uses Hn+, so the hyperoctahedral quantum group, as the quantum group providing the quantum strategy. And so in the talk by Pierre Botteron, you will also see more on graph games, but not only for classical and quantum strategies, but also for non-signaling strategies, which is even larger way of getting strategies. So this talk will be on Thursday, if I'm correct. Yeah. So Pierre is also here, and he will speak in detail about these other games. Okay, so this was on graphs, a short review of what might have been known before, or some additions by people from my group. Now I would like to come to hypergraphs, so the first generalization of graphs in this talk. So here's a graph. So a graph has vertices and it has edges, and each edge has one range vertex and one source vertex. Now for a hypergraph, you have hyperedges. So this means every edge can have multiple vertices as an input and multiple vertices as an output. So you have range and source map. Now they go to the power sets. For some reason, we exclude the empty set for the source, but we allow it for the range. So this is some technicality, which, if you want to learn more about this, we shall talk in private. But so this is hypergraphs. Basically, range and source now go to the power sets. And also here, I would like to speak about all these three aspects. So the first aspect was quantum groups. So in this case, quantum automorphism groups. There is a definition of quantum automorphism groups for hypergraphs given by Nicolas Faros. And here you see the definition. So you take also just some magic unitaries, but you take one magic unitary for the vertices and another one for the edges. So you're allowed to permute the vertices, you're allowed to permute the edges. And then you have this intertwining relations with the source and range matrices. So this is his definition of a quantum automorphism group for hypergraphs. So here's a picture of Nicolas and the archive paper where he introduced this object. And he, for instance, he showed that if you take a graph and you see it as a hypergraph in a natural way by saying, okay, the source and the range actually goes to the power set, it's just a one element set, then it generalizes the definition of a quantum automorphism group of a graph, but actually of the one of Bichon. Yeah. So he has some nice results here. So it's more detailed than what I'm writing down, but yeah, you can take a look at the paper. So we have this definition of the quantum automorphism groups of this hypergraph. Now we also have a definition of a C-star algebra associated to a hypergraph. So I defined this together with some students from Saarbrücken, Miriam Trieb and Dean Senner, who are not doing a PhD, so it's master's students. And so here we gave a definition of hypergraphs, hypergraph C-star algebra. So you see the definition, and if you recall what we had before, it's in black, and now in red I highlighted the changes. So now, for instance, these two partial isometries, SE star SF, they do not need to be just one projection, but they can be the sum over all projections in the range. So instead of single projections, now sometimes you have to work with sums of projections, because these hyperedges don't go from one vertex to another vertex, but from several vertices to several vertices. So this is the definition, and if a graph is seen as a hypergraph, then this definition coincides with graph C-star algebra, so it's an honest generalization. And the main point is that these hypergraph C-star algebras, they do not always need to be nuclear. So I don't know if you know about nuclearity for C-star algebra, so it's a nice approximation property, and all graph C-star algebras are nuclear, but these hypergraph C-star algebras, we have examples which are not nuclear, even examples which are not exact. So free products can occur, and well, I find this nice because it shows that this class is particularly larger than graph C-star algebras. Now the classifiers might find this frightening, because those who classify C-star algebras, they mainly classify nuclear C-star algebras, but not others. Still, I thought that it could be interesting because graph C-star algebras, they can be classified via methods of K-theory. And now if you have a larger class which looks like graph C-star algebras, it's pretty close to it, maybe you can still classify this via K-theory, and then you could classify a class of C-star algebras which is not nuclear. So this would be the hope, so this is one reason why we introduced it. And my PhD student Björn Schäfer, who's also here, he's hiding his green tag, sorry. So he studied nuclearity for these C-star algebras in detail, and he could show that they are nuclear if and only if you have a criterion on minors. So you define certain minors for these hypergraphs, and then you consider the C-star algebra of this minor, and if this has certain properties, then you can see that your hypergraph C-star algebra is nuclear. Okay, so that's a very nice work on this nuclearity for these objects. And also, we had before this theorem by Simon and myself that the quantum automorphism group of a graph acts on the graph C-star algebra. So we have the analog here. The quantum automorphism group of the hypergraph acts on the hypergraph C-star algebra. So this is another result by Nicholas, whom I just mentioned before. So this is also in his paper. And for us, this was relevant because we said, okay, we're not so sure about the definition for a hypergraph C-star algebra. I mean, you can define anything. So does it make sense? Of course, we want that every definition of a hypergraph C-star algebra generalizes the one of graph C-star algebras. So if you plug in a graph, it should coincide with the previous definition. But how else can you justify that it's a reasonable definition? Well, the definition of a quantum automorphism group of a hypergraph, we have the same problem, right? So we define some quantum automorphism group, but is it reasonable? I don't know. And since these quantum automorphism groups do act on the hypergraph C-star algebra, at least this is a hint that both definitions match in a way, right? So this is why we thought it's a good idea to develop these two things in parallel. So here generalization, and also the link between them generalizes, so we were happy. Okay, so this is on hypergraphs. So still a lot has to be done. So for instance, we did not compute the K-theory yet. So and also many examples are open. So we have studied it a bit, but not too much. And also for non-local games, I think we don't have non-local games. So here's a placeholder for anyone who's interested in joining. Maybe I should specify that the people should come from this workshop. Okay. So this is, feel free to join the work on hypergraphs. Now, another generalization is on metroids. So metroids, they generalize graphs and linear independence at the same time, which is a bit confusing when you read this for the first time, but you might have heard about metroids before, because they have a boost in their attention recently because there's been a Fields Medal for metroid work. So it's a thing that people like. And I'm in a collaborative research center with algebras, and they study metroids, and they really want to see a landscape of metroids. So for them it's still a bit mysterious, these objects, and they want to see some metroids behave differently than others. And then I said, well, maybe some of them do have quantum symmetries and others don't. Ha ha ha, and then we drink our glass of wine. But then they said, okay, now seriously work this out. So we sat down and we gave some definition of quantum automorphism groups for metroids. But now a problem arises. Namely, if you have ever worked with metroids, there are many definitions of a metroid, and they're equivalent, but this is not straightforward to prove that they're equivalent. So there are many approaches. Fortunately, when you ask for the symmetries of a metroid, it doesn't matter. So the symmetries of a metroid is independent of this definition, but our definition of the quantum automorphism group isn't. So it depends on the definition, which in the beginning we thought, oh, we make a mistake because we just want one definition. But then it's the same for graphs, right? I mean, for quantum automorphism groups of graphs, as I said, when you go to the quantum world, you have two different definitions, the one of Julien Bichon and the one of Theo Banneker. So maybe it's okay if here we also have different definitions. So here I listed some of them. I mean, these letters don't mean anything to you, but I just want to show that we have different definitions of quantum automorphism groups of metroids, and it's probably worth studying all of them. So this was something we did for these metroids. Now, associated C-star algebras, non-local games, we don't know. Again, this is open for you to join. And again here, it would probably be nice to have an associated C-star algebra and then let these objects act on it and then justify that all the definitions make sense. Yeah. So here's still some work to be done. It's just the first step in this direction. And also we would, of course, like to see more examples for these quantum automorphism groups and for the C-star algebras. So we're not at this point yet where we can draw very specific lines in the world of metroids by saying these behave differently than others. So this would be, of course, nice to see if a metroid has a certain property, then it does have quantum symmetries or something like this, vice versa. This would be the dream, but I don't know whether this becomes true. Okay, and the last generalization is then, of course, quantum graphs, but I will not give a talk on quantum graphs because there have been many talks on this already. So here we do know quantum automorphism groups. We do have these associated C-star algebras, which we call quantum Kunz-Krieger algebras. And we do have non-local games. So many things are done, but of course it's not yet finished. So it's a very young field, these quantum graphs. And if you come to the workshop, then you will get an overview on what has been done and what can be done. And in particular, I would also be interested in seeing how does it relate with the hypergraphs and metroids. I mean, hypergraphs and metroids are generalizations of graphs. Quantum graphs are generalizations of graphs. I don't know whether there's any link between it, but if you have different generalizations, you can ask what's the link. Maybe you can also define quantum metroids. I don't know. Okay, maybe this is not for this workshop. Okay. Anyway, thank you very much for setting up this conference. Here's a small overview. Here are the archive numbers. Thank you for your attention.
Thank you very much. Thank you for questions, suggestions. Indeed, that's
for these metroids, you mentioned there's various different quantum automorphism groups. Does any of them agree with the Banneker's quantum automorphism group of a graph, if you have a graph metroid?
I think we also talked about graph metroids in our paper, but I'm not so sure whether we really have no, I think, yeah, so the experts give me a sign. We don't know the link to the...
No, I think they don't coincide.
They don't coincide. Okay, so that's the answer. And
So I want to ask for hypergraphs. So for normal graphs, you have this, so that the action of the quantum algebra group in Banneker sense was maximal. And for hypergraphs, do you also have some kind of maximality? Because in a sense, like in the normal graph sense, it sort of suggests that the Banneker one is a nice one. But in hypergraphs, you said that it corresponds to the.
Sure.
So, okay, so could there be hope that there's a different definition that is maximal and generalizes the graph thing well, or is there really other problems? We'll just stop.
So if you want to have a detailed answer, you should speak to Nicolas or Björn who are here. But my short answer is that Nicolas, in his paper, he has a result that it acts maximally on the hypergraph C-star algebra if you take this action and also the action of the some opposite graph. So you have some additional conditions on the action, and then it's maximal. But I think, yeah, probably there's also another definition which is in this Banneker sense. But we have an idea of some other definition, but we don't have some action and maximality result for it.
On your matroid quantum automorphisms, or were those different labels indicative of the different definitions of matroids? So you can base this independent set.
Yes.
For the original Kunst-Krieger algebras, you had this 6-term exact sequence to K-theory. Anything like that for, let's say, the hypergraphs?
Not yet, yeah. So if you want to work with the K-theory of graphs, I think moves is one of the things that you typically use. So we have some definition of moves for hypergraphs, which is okay, but it doesn't behave as perfect as for the graphs. And in particular, we don't have some 6-term exact sequence yet. Yeah.
Okay. Well, if not, then let us thank Moritz again.